Good morning, guys. We're going to continue our discussion with Lesson 7.1, Solving Systems of Equations by Graphing. But today we're going to be looking at a couple application problems, word problems. We're going to see how they are used in the real world. Now, sometimes we have situations, two or three different situations, to where we need to know if, at all, the situations would provide the same results or the equal results. So let's look at this example right here. It says, the system below models the cost of taking an aerobics class as a function of the number of classes. Now what that means is that if you have two different aerobics classes that you would like to attend, they are of different costs, and we're going to see their equations in a moment. And of course, the more classes that you attend, the greater the cost is for attending those classes. It says find the solution of the system by graphing. Now after yesterday and the day before, you know to solve a system of equations by graphing, you simply graph the two lines and the solution is where the two lines intersect. Then they ask you to determine what does the solution mean in terms of the situation. Well, when we talk about the solution, we're going to be talking about where they are equal. So let's look at our system. Now, the first part, we have to look at the two equations. So we have C of A equals 2A plus 10. Now remember, this C of A is just function notation. That means the cost of an aerobics class. That's the same thing as saying Y equals. And then we have another aerobics class that is represented by this function, C of A equals 4A. Now let's make sure that we understand what this means. Now if you attend this aerobics class right here, it's $10 to start. It's almost like you're joining a club. And then after you pay your $10, it costs $2 per aerobics class. So every time you go to an aerobics class, it costs you $2. Or you can join a different aerobics class to where there is no upfront cost. You can see the y-intercept there is 0, but it costs $4 per class every time you want to go. So you would have to decide, am I only going to go to a couple aerobics classes, or is this something that I'm going to continue to do for a while? And you want to know what the best costs are going to be. Well, since the second aerobics class costs more per class, eventually its cost is going to catch up to and even pass what the cost is for the first aerobics class. Now, to find out where the costs would be the same, we're going to graph these. So let's look at our graph here. Down at the bottom, we have the number of classes. That's your controlling variable because we said the number of classes you attend controls the cost. The total cost is here on the side. Now let's graph this first equation, 2a plus 10. Well, your y-intercept is 10, so we had to put a point right there at 10 on the y-axis. And then the slope is 2, so that means rise 2 and go 1 to the right. Well, we're counting on this scale here by 2, so this is 2 and 1 to the right. We would put another dot right there and then draw our line. So this line right here represents the first aerobics class. Now let's graph the second function. Well, again, we see here that the y-intercept is 0, so we would put a dot right here at the origin. And its slope, or rate of change, is 4. So that means up 4 and 1 to the right. So we go up 4, 1 to the right. We would put another dot right there. And then we would draw our line. Now you can see here, since the two equations do not have the same rate of change, the first one has 2, the second one has 4, we know that these lines are eventually going to intersect because the rates of change are different. And we can see here in our graph where they do intersect. And they represented that that place with that point. And then they even gave you the solution here. They said that they intersect at 520. Now let's make sure we understand what that means. Here's 5 on our x-axis. We go up. And then we come over and read this value off the y-axis. So 5 on the x-axis, 20 on the y-axis. So our solution is 520. Well, that's all well and wonderful. What does it mean? Well, what that means is the 5 represents the number of classes. The 20 represents the total cost. So because they intersect at 520, that means that after 5 classes, the cost is $20 for both of the aerobics classes. That is the only time that these two aerobics classes are going to cost the same, is when you go 5 times. So you would have to decide which aerobics class am I going to join. Now, first of all, the quality of the aerobics class too plays into it, but let's say that you like these aerobics classes equally. So that cost is the only determining factor here. Well, if you're only going to go to an aerobics class a couple of times, well, then the second aerobics class is going to be the better choice for you because its cost is less. But if you're going to go several times, the first aerobics class is going to be the better choice because after 5 classes, we can see that its cost is going to be less. So you as a customer would have to decide how many times am I going to go? And then you would have to decide which class you want to take. All right, let's look at another situation. Well, the second slide here is interpreting the solution, which we already did. We said that after 5 classes, both will cost the same. All right, 2 friends are walking around a quarter-mile track. Now, before we read any further, you guys probably know that if you walk around a quarter-mile track, or like football fields is a lot of times what you guys call it, that is 1/4 of a mile that you walked. And if you walk around it 4 times, you guessed it, you just walked 1 mile. Okay? So 2 friends are walking around a quarter-mile track. One person has completed 6 laps before the second person starts. Now, if you walked around this quarter-mile track 6 times, we already said that 4 times is 1 mile, so 6 times would be 1.5 miles. So before the second person even started, the first person already walked 1.5 miles. Let's continue reading. It says the system below models the distance d of t in miles each walker covers as a function of time, t in hours. So they went ahead and they defined your variables for you. They said t represents hours and d of t represents your distance in miles. So they gave you the system of equations. Now in lesson 7.1, we're always solving these systems by graphing. Later on, we're going to solve by a different technique. So to determine, well, first of all, let's analyze the situation. We can see that that second person is walking at a rate of 4 miles per hour compared to the first person, 3 miles per hour. Well, if this person is walking faster, even though he started later, if they walk long enough, eventually this person is going to catch up to the distance walked by the first person. Okay, so to solve this system, to see how many miles they would have walked before their distances are equal, we need to graph them. So let's go ahead. So let's get some labels on our graph. Down here is time walked. That is our independent variable. We'll put our distance traveled on our vertical axis because distance traveled determines on how long you walk. So it's the distance traveled is your dependent variable. Let's get a scale on here. We'll count by ones. And we'll also count by ones on our vertical axis. Now you have to determine how big your scales are going to be depending on your problem situation. So let's graph this first equation. D of t equals 3t plus 1.5. All right, we know how to graph. We know that the y-intercept gets plotted first. So we have 1.5, so we put a dot at 1.5. Then we come over here and we look at our rate of change. Our rate of change is 3, so that means rise 3, go to the right 1. Now we always start from where we left our y-intercept. So since it's at a half mark, when you count one whole one, you're still going to be at a half mark. So watch. We go up 1, 2, 3. So right here, by going up 3, we're between 4.5. So we went up 3. Cursor disappeared. We went up 3, and we have to go to the right 1. So we're going to put a dot right there. And then draw our line. So the red line represents the first equation. Now let's go ahead and graph our second equation. We can see that we have no y-intercept, so that means we're going to put a dot right here at the origin. And we can see that our rate of change is 4, so that means go up 4 and to the right 1. So 1, 2, 3, 4, and to the right 1. So we're going to put a dot right there. And then draw the line. So we can see that our graphs have intersected because we knew that they were going to because our rates of change here are different. Remember, the only time they won't intersect is if the rates of change are the same value. But since these rates of change are different, we know that they will intersect. Now, here's a word of caution whenever you're graphing these. If you should graph both of your lines and they don't intersect, you have to ask yourself a question. Are the rates of change the same or are they different? And if the rates of change are different and they didn't intersect on your graph, that just means that your graph either isn't big enough or you need to change your scales so that you can see that where they intersected, because eventually they will intersect if the rates of change are different. So you would have to make some adjustments in your graph. Alrighty, so we graphed. We can see that they intersect. Now the lines are very, very close together, so it's a little bit tougher to see exactly where they intersected, but we can follow it along. It appears that they intersect about right there. Now, keep in mind, we are human, and when we graph, we have a little bit of human error in graphing, so we have to take that into account. So that's why solving systems of equations by graphing is not always the best method. But they appear to intersect right around in there. So we can see that they intersect there. So let's interpret that solution. What that means is that at 1.5 hours, because remember time here is in hours, we can go up and we can see that they intersect around 6 miles. So after about 1.5 hours walking, they have walked the same distance of about 6 miles. Okay? So, and that's your solution. We've interpreted that solution. After 1.5 hours, the friends walked the same distance of 6 miles. And that's it. That's all there is to solving these application problems.